Okay, welcome everybody to the first BSV Academy webcast. We're going to start doing more of these on a regular basis, covering topics that hopefully will help you as a developer, an entrepreneur, or just someone interested in the space. We, want to use these webcasts as an opportunity both to answer questions. So be sure to ask any questions along the way, and we'll have a Q&A at the end. But then also cover topics that may not necessarily need us to develop a whole course around, but we want to help people think differently about something. So in this course, or in this webcast today, we're going to talk about Bitcoin transactions and specifically thinking differently about them from the sense of how do they work from a fundamental level, and hopefully getting you to think outside the box about how to leverage locking scripts and unlocking scripts to create new types of transactions. So we're going to put this on the screen here and get started. So this is generally roughly our agenda today. Like I said, we want to think differently about how Bitcoin transactions work from a fundamental level, how Bitcoin script works as a predicate, and then generally, what is a locking script, what is an unlocking script, how does that fit into a transaction? And then we will tie it all together at the very end to form what is colloquially referred to as a standard Bitcoin transaction. But hopefully by the end of this, you'll kind of have some feeling for what standard means and what it doesn't mean. Okay, so the first thing we want to cover is the white paper. The white paper, you may hear my dogs barking throughout this because they're psychotic. So the white paper defines transactions in section 2 of the white paper, where it says that we define an electronic coin as a chain of digital signatures, and then it has a graphic to display what a transaction is. Probably not surprisingly, this transaction or Bitcoin white paper pretty much defines a paid to public key transaction. So it's not surprising that most people, when they think of Bitcoin transaction, think of just sending coins to a public key and then using the corresponding key to create a signature to spend those coins. It's all spelled out right here. It's a general just pay to public key transaction. And the other thing I guess that's important here is, obviously the idea of making digital cash transactions wasn't necessarily new, but as you might be familiar with, pretty much every previous electronic cash solution required that central mint to be aware of all the transactions that were out there to prevent double spending. And obviously the innovative thing about Bitcoin is the ability to prevent double spending without the requirement of a central mint. Again, the white paper is defining a very specific type of transaction called pay to public key, but this is not meant to be the only type of transaction that you can make with the system, as we're going to see from in a little bit here. And the other part of the white paper that's definitely relevant to us is section 9, where it talks about combining and splitting value. So basically what this is saying is, it could be possible that we want to handle all 21 million coins, 21 million, whatever Satoshis individually, but it would be very hard for us to do that. So the way that we handle this instead is every transaction can have multiple inputs and multiple outputs. As far as I know, there probably is a limit, but there's no theoretical limit as to the number of inputs and outputs that can exist in one transaction. And generally, as a standard of practice, every transaction will at least include 2 outputs, one for the payment and then one as a change output back to the receiver. So the way that this could work, I think I have a better image here. As you see here, we have 4 different transactions, some of them dependent on others. So in transaction A, we have 2 inputs that create a 6.102 Bitcoin output. In transaction B, we are creating we actually have a Coinbase transaction. So the coin started as mined from or created by a miner, and then put into an output that then is used as an input for transaction C. So we have 2 different inputs and then multiple outputs in transaction C, and so forth and so on. So we actually create a DAG, across all these different transactions. And that's generally how this is supposed to work. And the important thing for us, obviously, is that this so-called back to Genesis problem is not a problem in Bitcoin. We don't need to know of an entire transaction's history to use it. And this ability to have multiple inputs and multiple outputs is going to be very relevant for us as we move forward in this webcast. Now, one important thing to keep in mind that if you are coming from the rest of the blockchain ecosystem, you might be aware of is that Bitcoin uses the UTXO model of record keeping, which is different than Ethereum's account-based model. This makes, I think this main fact is what makes it very hard for some developers to wrap their head on how to do complex transaction types in Bitcoin. Because if you do come from the Ethereum world, you're probably used to having a smart contract address. Everything runs through that address, and that might seem nice and clean, but that comes with a sacrifice of scalability. So the reason why Bitcoin uses the UTXO model is enables scalability. What is UTXO? It is an unspent transaction output. So if we look at this previous example, we actually have two UTXOs. If this is the current state of the blockchain, we have two UTXOs. We have this change output here that is unspent, and then we have this output here that is also unspent. In order to spend a UTXO, you need to have a corresponding unlocking script that is valid for the locking script of the UTXO. And we will talk about that in 1 second. But again, the important thing I want you to think about here is that a lot of people don't think that you can do complex transactions and smart contracting in Bitcoin, but you can. It just, like I said, requires us to think a little bit differently than what some of the other blockchains preach about. And then before we kind of get into the nuts and bolts, I do want to at least mention this piece, because this is something that's really important for us to think about as we build new transaction types, new transaction templates, and we think about transactions themselves. So the other relevant piece of the white paper is section 10, where we talk about privacy. And in this new privacy model that Bitcoin introduces for transactions, we firewall identity from transactions. So it even says that obviously with multiple input transactions, there's going to be inevitably some linking that occurs. But we don't have to. We can actually firewall off identity, and we can have a great level of privacy, especially as more transactions occur. The other important piece that is mentioned is we should not be reusing keys. So keys should be a one-time use to spend UTXOs in the traditional sense when we have public keys that hold coins. We should only use them one time. So any wallets that reuse keys is not a very good wallet. And the other thing is that privacy increases with scale. So another benefit of the UTXO model is that as we scale unboundedly, privacy becomes an NP-hard problem for anyone that's trying to link every transaction together. It's nearly impossible. Okay, so we've kind of covered what the white paper is relevant for us here, but actually it does not have all of the details, because something that's never mentioned in the white paper, but is incredibly relevant if you're a Bitcoin developer or just interested in Bitcoin, is the scripting language. So the scripting language was released with the initial source code, but there was never any mention of it in the Bitcoin white paper. But we do have a lot of quotes from Satoshi Nakamoto himself that gives us some insight into what the purpose of script was. I almost want to just read this all word for word, but I'll let you do that while it's on screen. But I'll pick out some important parts. So the first, obviously, that is our guiding thesis in BSV is that the core design was set in stone for the rest of its lifetime when version 0.1 was released. So that is an admission by Satoshi Nakamoto himself that it was very important that the rules were set when Bitcoin was released, because he didn't want the ability for the rules to change. And that's very important for any monetary system, but we're going to find even at the end of this, he talks about why that might be important from a software perspective as well. But because of that, he designed it in a way to support every possible transaction type that he could think of. He even says, I think towards the bottom, the design supports a tremendous variety of possible transaction types that he designed years ago. So we've clearly been working on this for a while: escrow transactions, bonded contracts, third-party arbitration, and multi-party signatures, and etc. He says, if this all catches on in a big way, these are things that we'll want to explore in the future, but they all had to be designed at the beginning to make sure they would be possible later. Well, luckily for us, it has caught on in a very big way. So we are going to explore that today. The other piece that's very relevant to us, which I think I put on the next screen here, is that the script is actually a predicate. So it's just an equation that evaluates to true or false. But since he says that predicate is a long, unfamiliar word, he called it script. And so this is actually quite simple. So even if you aren't familiar with what a predicate is or anything like that, it's quite simple. If the equation evaluates to true, then we will allow spending of the coins. And if the equation evaluates to no, then the transaction will fail and the coins cannot be spent. This is really simple, but again, some other technical details about Script is that it's very similar to an older programming language called Forth, and it's a stacked-based language that is last in, first out. So the last thing put into the stack is the first thing to come out of the stack. This, again, relevant if you have studied computer science, but even if you haven't, you're not going to need it for the purposes of this presentation. We are not going to get super into the nuts and bolts from a development perspective on how to do this. I think hopefully, even with no computer science knowledge, you should be able to follow along here as I go through some of these examples. So now we've introduced the mechanism for how we can build these equations, but how do they actually look in a transaction? So every transaction is made up of locking scripts and unlocking scripts. A locking script is basically sits there for an output, and it's some equation basically that you have to solve in order to spend the coins in it. If any transaction exists in the blockchain, then that means that the unlocking script used to spend any of the outputs in the transaction had to be valid for the corresponding outputs locking script. And the reason why we know that is because it's a predicate. So the miners will only accept a transaction if the script interpreter evaluates to true. So we know that because it evaluates to true, it has to be valid. So let's break these down into two components. The locking script is commonly referred to in most of the programming libraries that you see as script pub key. And the reason that this is that obviously we mentioned at the beginning the standard transaction type of paying to a public key. Well, in a standard transaction, the locking script is basically an equation involving the public key. And what we are saying is that, that's the padlock. So the analogy here would be some kind of padlock where if the combination is provided to script pub key and it's correct, then the coins in the UTXO can be spent. Obviously the corresponding analog to this for the unlocking script would be the combination itself. So in dev speak, that's usually called script sig. And that's because we require a signature from the corresponding private key to the public key to unlock coins locked up to a public key. So when transactions are evaluated by the script interpreter, we actually load script sig onto the stack first, and then we load the outputs locking script. And if at the very end true is left in the stack, then the transaction is valid and the locked coins can be spent. We're going to start with a very simplistic example. So this is what I hope you leave this webcast with the mindset of is that while we've kind of revolved Bitcoin around the standard use case of a signature corresponding to a public key, and then that's how everything works. We need to start instead from the building blocks of predicate true false. So if we evaluate to true, then the coins can be spent. If we evaluate to false, the coins cannot be spent. So the most simplistic way of doing this would be to have a math problem. So let's say that we have fifth graders or something, or however old you are when you're addition, and you say, look, I'm going to really make sure that you learn your addition, and I'm going to lock up $5 in this UTXO that says, find me two numbers that add up to 16. So we can do this quite easily in Bitcoin script. So the locking script is going to be op add, op 16, and op equal. And I'll explain why it's written this way. But if you remember, we said that the unlocking script is loaded onto the stack first, and then the locking script. And so we're going to walk through this step by step here. But again, I create some output that has this locking script. I'll lock up $5, or if I'm really trying to motivate my child, maybe $100 or something. And in order for them to spend it, they just have to find any two numbers that can add up to 16. So we're going to try 12 and 14. So the very first thing that happens is we have an empty stack, and we're going to unload the locking script 12 and 4 first. I think I can draw if I'm not mistaken, but maybe not. Let's see. maybe not. I don't want to waste time drawing or trying to figure out how to draw, but I will. Maybe you can use see my cursor here. First on the stack, or first thing we're going to do is combine the unlocking script and the locking script. So we have 12, 4, op add, op 16, op equal. You don't need to care about Bitcoin script to understand that this is right, but it just is right. And you can, I'll make sure there's a link to the Bitcoin SV wiki in the description of the video, which will, you can look at all the op codes and how they work and start letting your imagination run wild. But the next thing that happens is we're going to load in order each opcode or data piece onto the stack. So first we would load 12 and 4 onto the stack, followed by op add. And when op add is evaluated, it is going to take the previous 2 inputs and add them. So I've just simplified this for our purposes here. So now while the script that has yet to be loaded onto the stack is 16 equal, we have 12 plus 4. Then we evaluate 12 plus 4, which is 16. And then we load 16 onto the stack, and then we're going to check if they are equal, and then we're going to end up with true. So if I were to try to spend that output with the unlocking script 12.4, then this would work. If I tried 12.3, then I would end up with 15.16 getting evaluated by op equal, which would fail, and the coins would not be able to be spent. So that was like the most simplistic example that we could think of to use Bitcoin script to incentivize the solving of a math problem. But obviously Bitcoin script is not limited just to addition and multiplication and division. So we're going to have another incentivized example. Maybe I am a geography teacher, and I want to say, what is the capital city of the United States of America? So I'm going to be very, this is very realistic because you can't actually use, Bitcoin script doesn't evaluate actual strings. It would use hexadecimal. So I took the hexadecimal of Washington, D.C., which is this long string here at the top. And then I'm going to devise some locking script. But of course, I don't want to expose the answer maybe in my locking script because then that would give it away. So instead, maybe I would hash it to another value, which I think I did on the next page. So I took the double SHA-256 hash of Washington, D.C. and put it in my locking script. And then let's say I'm a very smart student and I really want the money that's locked up in this question. So my unlocking script here would be the very first element on the stack, which is the hexadecimal string for Washington, D.C. And then the locking script is going to double SHA-256 hash that value and check it against the hash value that I've created here. So this is, again, very, very, very simplistic. But I'm going to try the answer of Washington, D.C. The locking script would then evaluate that double SHA-256 hash and then equate it to the locking script that was loaded, and we evaluate to true. Ta-da, right? So instead of just simple mathematical addition problems, we can also have more complex problems. Like in this case, it was a very simple word problem. Give me the correct answer to this question. So bitwise operators exist in Bitcoin script. There's a whole host of other opcodes, but again, remember, I'm going to go all the way back to this very long post made by Satoshi. He was very clear that this is always the intended. This is what we always wanted, right? We always wanted the script to be universal enough to support any kind of transaction type that you want to create. Of course, we've done very simplistic examples, but we're showing that Bitcoin script is just a predicate language that enables you to lock coins in any arbitrary constraint. And as long as the constraint is satisfied, those coins can be unlocked. So we can get even more complex here, right? So what if our problem has multiple answers, right? Maybe our example here is going to be, what is the first or last name of the creator of Bitcoin? Of course, there would be 4 answers here. I actually only use 2, but I'm actually not going to use hexadecimal for this just so that you can follow along a little bit easier. And I actually never checked this script, so there's possible the script is wrong, but I'm pretty sure it wasn't. I made it very quickly. So we're going to try the answer Nakamoto, and then our locking script is going to be everything starting with opdupe. And so basically what this script is going to do is check, okay, well, the answer can be one of either Satoshi or Nakamoto. So let's duplicate the answer that is given and check it against both Satoshi or Nakamoto. And then we can just walk through this step by step here. So, so first, it's going to duplicate Nakamoto. As you can see here on the left, opdupe is going to just duplicate the top stack item. And then we're going to end up with Nakamoto. We're going to load Satoshi onto the stack and then check if it is equal with the other top stack item. It takes 2 inputs. And since the strings are not equivalent, it's going to leave false on the stack. And then we're going to evaluate opIf. And the way that opIf works is if the top stack value is true, then it performs everything that is in the middle between it and opelse. And if it is if false is fed into opIf, it will evaluate everything between opelse and opendif. So what we're going to see here is opIf is going to see false on the stack. So it's going to move all the way to the block that starts with opelse. It is then going to load Nakamoto and opequal onto the stack and check it. And we're going to be left with true. So we've created another incentivized word problem of, give me the first or last name of Satoshi Nakamoto. Of course, I would probably want to hash these values because when I create a locking script, it's public to the world. And then I would want to hash whatever is sent into the unlocking script to check it. But this is, again, a very simplistic example to help you understand how this works. So this is going to bring us to the standard Bitcoin transaction. So again, everything that we've done up till now has not looked at all like what the Bitcoin white paper spelled out with the pay to public key transaction. Instead, actually, we have just been showing from first principles how Bitcoin script acts as a predicate, how we can lock coins into some mechanism. My analogy would be like a padlock, and then the corresponding combination can unlock it. So this leads us all the way to the very first standard use case that is outlined in the Bitcoin white paper, except it's slightly modified because in the white paper, we don't have a key. So there is another Bitcoin transaction type that is just pay to public key. But the most common Bitcoin transaction type is pay to public key hash, where in the locking script, we have a hash of the public key. And then obviously the unlocking script is going to be the signature corresponding with the public key. And the reason for that has to do with op check sig. But again, in this standard transaction type, this is what, according to the world, makes Bitcoin work and how it has worked for 12 years. The padlock is just a hash of the public key. The combination is a signature associated with a public key, which can only be created if you have the corresponding private key. And this is, a very great use case of Bitcoin if you just want to send money around between public keys. So we'll just step through this very quickly to help you understand how it works. So remember, our unlocking script is loaded first, and then the locking script. And basically what this is going to do is check the public key against the hash that is in the locking script. So it's going to check equal verify is going to do op equal on them and then drop the stack item if it's true. And then we're left with just the signature and the public key where check sig will be evaluated. And so basically, we're not going to get into all the nuts and bolts of check sig, but check sig is going to check the signature against a pre-image of the transaction. And if that works, we're going to end up with true. So what you see here, what we've done here is start with Bitcoin script as a predicate. We've stepped through it from a very simplistic example of an addition problem all the way to an if-then statement. And now we're left with this standard transaction type. So what we can actually start doing as we get more complex, which we won't cover in this webcast, but in future webcasts, is we can combine the use of signatures and complex logic to enable more complex use cases. So let me go to the next. So what this means is that we have, all sorts of things in the locking script, right? So we can have hash puzzles. We did have a hash puzzle example in our second example where I asked for the capital of the United States. A hash puzzle can be used for a multitude of things, right? But if our goal is basically just prove that you have X and I hash X and put it in the locking script, then that would enable you to spend coins. We can also do things like R puzzles. So R puzzles, I was going to cover, but I didn't want to get too complex. The goal here is an introduction to transactions. And what an R puzzle is basically the ability for us to use a knowledge proof of an element of a signature, which is K. And so what we can actually do is any signature that is made knowing K can spend coins. So this is has many different sorts of use cases, but the important thing is that the way that R puzzles work is they actually take the signature from the stack and then they do some mathematical operations on it to pull R out of the signature, the R value of the signature. And so that means that we can actually do all sorts of different things in Bitcoin because we have the signature on the stack. We can manipulate it. We can do a ton of different things, which again will be the subject of future webcasts to enable a lot of complex use cases. And then this means that we can do things that are so popular in all sorts of other blockchains, which one of the most common ones is zero knowledge proofs. I'll also be putting a link into a lot of the Scrypt articles that are out there that cover this kind of stuff. But I think it was a great article either today or yesterday. He just wrote, I think it was a part 2 on zero knowledge proofs. But what you can kind of see here, because we have this predicate language and we have the scalability of the UTXO model, we can have all the complexity of Ethereum and Solana and all these other blockchains, but with the scalability of Bitcoin. And the important thing for us to be thinking about right now is that scripts can be arbitrarily simplistic or complex. I really encourage you to think differently about how these things can work. There are, what will be the subject of some future webcasts is that in ECDSA, we have all these different hidden secrets that are just innate to cryptography that can enable more complexity than meets the eye, right? So I think one of the biggest, an interesting, I guess, mistake that the BTC developers have made is that they've kind of assumed that ECDSA has these terrible properties to it that things like Schnorr and Taproot can fix. We actually do all these things inside of Bitcoin. And also the nature of ECDSA also enables different types of complexity that isn't possible on these other algorithms. And then lastly, if you are a generic blockchain developer or whatever you want to call yourself, what you should be doing is utilizing the Bitcoin UTXO model for infinite scalability, or I guess what Craig would say is unbounded scalability. While it's maybe a little bit more complex to think about in terms of how to create a smart contract or how to do these different smart contracting techniques that you're used to in Ethereum, the UTXO model has in it scalability. And as we just saw through this webcast, is Bitcoin Script is capable of doing all the things that you want it to do. It just requires you to think a little bit differently. And luckily for us, we have things like Scrypt to compile native JavaScript, Golang, and C++ down into Bitcoin Script. So you don't have to worry about what Bitcoin Script is doing. But I think it is worth being familiar with how yacht codes work and from building blocks, how transactions work so you can create these different complex use cases. Okay, so that's the end of the presentation. This was just an introduction. We're going to take questions if you have any, so go ahead and post them in the chat. We have someone monitoring for chat, and we're going to bring them onto screen. I'm going to pull this off the screen. And I just want to say, again, what are my dogs' names? So my dogs' names are Milo and Madison. One of those because I used to live in Madison, Wisconsin, but I don't any longer. Okay, so we have a good real example of why you need a locking script use case. Yeah, so so hopefully you did see this question may have come in before we went through some of them, but again, these were just examples I came up with basically just on the spot. So what I hope this helped encourage you to think is, okay, well, if I want to incentivize the solution to a problem, then basically the answer to this is build a locking script that requires that solution as the quote unquote combination to the padlock, and then put it out there, right? So what we can actually imagine this being used for in the future is, for example, like data reduction, right? So if you have some large data set that you need some analysis done on, you could create locking scripts that requires the reduction to be done on that data, And then if the requirement is satisfied, you can submit the data and then receive, payment directly from the UTXO. So, that's just like one just again, off the top of my head, example of like, why would you want to build these different complex locking scripts? It's for us to build some kind of incentive into solving the problem. And there's all sorts of companies and wherever else that are using that simple concept. But so we did an addition problem. If you want to incentivize first graders or your child, we did a simple bitwise example, which is basically just give me a string that satisfies the answer to this question, and then a very generic if-then, but again, showing that we can do if-then statements inside of Bitcoin as well. All right, we'll go to the next question. So how does SegWit change the predicate mechanism? I don't think, I got to be honest, it's been so long since I even thought about SegWit. So that is a good question. I don't think it actually changed anything about script. I think it did something about like removing the signature from maybe evaluation in script. I'd have to follow up on that. That's actually a good question. I don't really remember what they did. It was so irrelevant to me at the time. Yeah, good question. Something with removing the signature. I don't know the technical details off the top of my head, but I can follow up on that. Okay, so how many transactions are needed to get the coins unlocked finally, including 4 to lock? Not sure when that question came through, but maybe if I could just give an example. So in any of these examples, it would just take one transaction to spend these coins. So in the case of, let's say even the most complex one here, the if-then, I would just want to create one transaction. Remember, when a locking script is created, let me take one that maybe spells this out better. So in the addition example, so the locking script here is up here. I just need to take that UTXO, add it as an input to my transaction. Let's say the output of transaction B has that locking script of an addition problem for giving 2 numbers that add up to 16. Then if I take that output, I would just want to say, okay, I'm going to build a new transaction, add it as an input, insert my unlocking script here, and then I would have however many outputs to spend the coins and wherever else. But it just takes one transaction to spend any UTXO. And theoretically, right, maybe this output is my bitwise example. This output is my, you can't see my cursor, I don't think. So let's say, the top output is my bitwise example, and the bottom output in transaction B is my addition example. Basically what that means is that in transaction C, I would actually have 2 different unlocking scripts for my 2 inputs, right? So the first input, we have the unlocking script that says Washington, D.C., and the second red input would have the unlocking script of 12 and 4. So it would just be one transaction, but obviously you would be creating the transaction with multiple inputs. And that, again, is spelled out here in this combining and splitting value section. So that's really a big benefit of the way that the UTXO model works, is that one transaction can have an arbitrarily large amount of inputs and outputs. I hope that answered that question. Okay, is there a way to write a locking script without knowing the final answer? So yeah, definitely. Probably another good question, right? I mean, that to me is what is probably more exciting, right? Well, I guess let me think about this. I'm trying to think of a real world use case, right? So obviously I could right now come up with some example of like check a signature against some random value or something, or that's probably not even a good example. Maybe there's some value that I don't know about, but I can just create some locking script that generates some random value and says, give me the hash of that value or something like that. So yeah, definitely you could create locking scripts that you don't know the answer to. I'm trying to think of what would be a good real world use case for that. And I'm sure there's some, even my data reduction example would probably be a good example of that, right? But I'm struggling to think of exactly what that would look like. But I bet there's someone that is thinking about this in the comment section that can think of one off the top of their head. And I encourage you to post it. Also, I'm glad to know you can see the cursor. I didn't realize that, so that makes my life a little bit easier. So smart contracts are possible using script only. Yeah. So the answer to that is yes. But remember, script is basically just the native. Let's see, let me find a good slide for this one. Script is just going to be the native predicate language for how you would program this, right? So you could theoretically use any higher level language like script to. So maybe you would write the smart contract, even if you wanted to write the smart contract in Solidity, if you're an Ethereum developer, then you can use the recently released transpiler to transpile the Solidity code into Bitcoin script or script code. But eventually, yeah, it's all going to get boiled down to Bitcoin script, which is just an assembly language. So yeah, because Bitcoin script itself is the way of that Bitcoin transactions are programmed, then you would have to use it. But the best part about companies like Scrypt, which again we'll put some links in the description, is that they act as a compiler, so you don't need to be familiar with the Bitcoin script language. Just like you probably aren't familiar with the assembly code that runs on your computer now, but you're familiar with JavaScript or Golang or whatever else. In the same way, you don't necessarily need to be familiar with the nuts and bolts of Bitcoin script. And really the purpose of covering that here today is just to, I think, show from building blocks how this stuff works and hopefully help you just think about this differently. Okay, so another great question. So why is Ethereum's account model not suitable for massive scalability? So the main reason is basically because a smart contract address on Ethereum has some logic to it. Everything that runs through that address has to be validated by every node on the network. This is essentially the problem with the belief that all nodes in the network matter and everyone needs to run a node and all that kind of stuff. So basically, every computation that occurs in the Ethereum network is done by these smart contract addresses. It's run through these same addresses, and every node in the network has to evaluate that computation. And that's part of the reason why it's so expensive to use the network and why it requires some kind of central planner to determine the fee rate in the network. And I'm sure someone has done way better. I'm willing to admit when I don't know something that well. I'm sure someone has done more research as to why it specifically is bad for scalability. But the important thing for us is that the UTXO model is built for scalability. So it's built for the ability for the miners to not care what is in the script. All that happens is they know if the script evaluates to true or false. And I think actually that's actually covered as well in this Satoshi quote. So the middle paragraph here, the receiver of a payment does a template match to the script. But eventually, nodes in the network don't even need to care about the template. If they want, they can just verify and process any new transactions into the block, even though they may not know how to read them. The script will evaluate to true or false just by nature of validating the transaction. Yeah, I feel like I went in a separate direction there, but basically, the computation doesn't have to be done by every node in the network. It's just it's a simple predicate, true or false, that is evaluated every time a coin is spent. Hopefully that helps. Maybe not. But follow up with me if that wasn't enough, and I can get you some more details. Okay, so do miners on BSV process any kind of script now, or only certain standard scripts like BTC and BCH? Yes, another great question. In BSV, there's there's definitely no constraints from a protocol perspective on how many opcodes can exist in a locking script, or how big a script can be. There are minor policy settings that might restrict that today, but for the most part, you can create any kind of definitely any of these examples that I just showed you. You could create a transaction that does that today. It would work. You can create much more complex scripting locking scripts to input them onto the network. So definitely the benefit of BSV is, number one, that we've restored all of the original opcodes. So there are opcodes that are disabled on Bitcoin Cash and BTC that enable you to do a lot of these complex things. Those are completely restored on BSV. We restored to that original protocol that was talked about here in this quote. And there are definitely scripts that could have been created in 2008 and 2009, for example, that aren't valid on BCH and BTC anymore, but would still be valid on BSV just because we've restored all those opcodes. Good question, but yes, pretty much anything that we do can BSV can handle just about any script possible now, and if it can't, you just need to talk with a miner to get that done. Okay, so another good question is, how do you unroll loops when the limit of the loop is variable? So if I'm understanding your correct question, basically you're saying you can't have an infinite number of loops that occur, right? So maybe I have like 20 op ifs that are evaluated. Yeah, you would have to essentially unroll the loop with some defined number of how many times you want to unroll the loop. But that's actually okay, right? That's pretty much how all programming works. Generally, you don't have something that runs, really not great code will have an infinite number of loops. You don't want to get caught in an infinite loop. If I'm not understanding your question correctly, you can reword it. But yeah, so basically, you would unroll loops using op if. There's really 3 different ways you can unroll loops in Bitcoin. I won't cover all of them right now, but I can definitely point you to some other details. But yeah, the easiest way would be just to essentially feed, let's say, a number of like 20 loops, and then evaluate 20 different op if statements, for example. So yeah, the limit of the loop is going to be variable, but or is going to be fixed, right? It's not, you can't have something just run in perpetuity, but that's not necessarily a bad thing. I hope that answered that question. Okay, so I think we are not going to take any more questions unless there are any, but I don't see any. So thank you for joining us again, this is our first BSV Academy webcast. We intend to do many more of these regularly. And I think this will be really valuable for covering stuff that don't require us to write a whole course for. But if there are any topics that you want us to cover, definitely feel free to send them to me at connor@bitcoinassociation.net, or just tweet at me or tweet at the Bitcoin Association Twitter account, or just get in contact, or join the BSV Discord channel as well, and let us know. So all those are very viable ways of getting in touch. So thanks for joining. I hope this was valuable, and we will see you at the next one.